we're officially live. Okay, so those two triangles, their areas are proportional to their bases. Now, there's also another set of triangles that have the same height, different height than these guys, right? But they share the same height, and they have the same bases A and B. What triangles am I talking about? What triangles am I talking about? They have this height in common, and they also have bases A and B. So what I'll write is this. They're also going to be proportional to A over B.
Are you talking about ABF?
A, B, F, this triangle here?
Yeah.
Ooh, that's a good thought. But ABF, while it does look like it could have the same height as this triangle over here, not quite necessarily. And then also, it doesn't have base A, it has base A plus B, right?
AGD and BGD?
AGD, yep, this triangle right here, this bottom triangle, right, it has a base A. And it has the same height as this triangle here, right? We know that because they're part of a bigger triangle, right? Bless you, Bo. So these two triangles also go together. So I'm going to say that their areas are proportional. So the area of triangle, this one right here, ADG, is proportional to the area of this triangle over here. I'll use like a minty green. Area of triangle BDG. So is everybody cool so far with where I'm getting these triangles at? Do we see where they're coming from? It's a lot of letters, I know. But all I'm saying is that the big triangle here with the red height and the big triangle here with the red height, they're proportional to their bases A and B. And then the small triangles here and here both have the same height. So they're going to be proportional to their bases A and B. Cool. So really what I'm saying is I could write this all as one equal statement. I could say this over this equals this over this equals this over this, right? So I have a proportion equaling a proportion equaling a proportion. That goes back to our first lemma, which says that if we have three proportions all equaling each other, then I can do subtraction, right? And have it equal the third guy. So that's what I'm going to do. So I'm going to write these as subtraction. So this equals that and that equals that. That means these equal each other. So I can put them in subtraction and have them equal A over B. So I'll write that and then we'll talk about it. So area of the first set of triangles in proportion. Let's do a big bar. So by our first lemma, we know this to be true. And what's beautiful about both these lemmas is you don't have to tell me why they're true. It's just by algebra. That's how we did these other ones, right? We did this by algebra, and we did this one by algebra, basically, right? Things just canceled. So they're not theorems or anything. They're just true. So you get all this for free, essentially. Cool. So why? What's the point? Well, here's the idea. Look on your diagram. The area of ACD, that's this big triangle right here. I'll highlight that. Minus the area of ADG. That's this triangle right here. What's something we could substitute for that? Big blue minus little blue. What's left over? The area of the big triangle minus the area of the little triangle. What?
CAG.
CAG, yeah. Triangle CAG is really what that means, right? You see that? This really is just triangle CAG. So CAG must be proportional to A, and by the same logic, this triangle over here must be proportional to B. We couldn't have done that before because A and B aren't those triangles' bases, right? But it turns out it's true. They will be, because this is the same thing as this triangle right here. And this will be the same as this triangle right here. So, therefore, triangle, the area of triangle ACG is proportional to the area of BCG. Ooh, yes. Sorry, I zoomed in a lot. Let me zoom out. Diagram's small, but the writing's big. A over B. Cool. Bless you. So I did all that to get these two triangles proportional to these two bottom parts of my triangle, right? Those aren't the bases of those two triangles, but they will end up being proportional. And I've proven that with my first two levels. Now we're going to do by the same dumb logic. Yeah, what's your question?
Are the two bottom ones, are they two different colors than the ones up there? Like the ACG and the BCG are just supposed to be different colors?
Yes, these are supposed to be these colors.
Okay.
Does that make sense? They're all similar shades of blue because they're all related in that regard. That's the artistic creativity I'm doing
Okay.
here. And then these are all similar shades of green because they're all related in that regard. But yeah, this is a different shade than this and this and this. But they're all related to B, right? And these are all blue, more or less. What? You okay? Okay, all right. So we know that this is A over B. Now, by the same logic, and let me get a clean diagram, I'm going to do the same thing for all the other triangles. So check it out. We just got these two to go with A and B. By the same dumb logic, this and this, these two triangles, would go with C and D. And by the same dumb logic, this and this would go with E and F, okay? So I'm going to write that. Does everybody see that? I'm going to do it again. Get my fingers out of the way. This triangle here and this triangle here, right? Big guy here, big guy here. They went with A and B, right? If I turn the diagram, maybe it's easier to see. This bit here and this bit here must go with C and D then. And then this triangle here and this triangle here must go with E and F. It's by the same logic, right? I'm going to get the whole thing here. I'm going to subtract this amount because this has a base of F and this has a base of F. That means this thing should be proportional to F, right? This has a base of E and this has a base of E, so when I subtract them I get this triangle. So this is going to go with E. Are we seeing that or are we not? Seeing it's the hard part. Are you with me? If you are, that's amazing. If not, tell me. I know. Michaela?
I'm mostly with you.
Generally see what I'm saying? Okay. Courtney?
Sure.
Okay. So, same dumb logic. Other sets of triangles. Let's talk about them. So, on here, so we can see a little bit better. Here's C and D. They're bases of these small triangles right here and here, right? But they're also bases of the big triangles here. So if I take a big triangle and I subtract the small triangle, I get this, right? You cool with that? So that's triangle ABG. And the other one would be triangle ACG. So ABG, ACG. Likely story. So let's do area of triangle ABG. Remember, ABG is this. ABG, it's this triangle right here. It goes with C. And then this triangle here must go with D. Area of triangle ACG. Oh, no, sorry, you can't see. All right, pink triangle went with D. Orange triangle went with C. And the reason for that is full thing minus this little guy leaves this. And we know that the little guy and the whole thing are proportional to C.
Move your headphones over to here.
Are you okay? I would not try to color everything like I am up at the top. I think that'll get confusing. The colors are only going to help if you're watching while I color it, because otherwise you're going to look up here and be like, wait, what? There's millions of colors everywhere, right? But if you watch while I color it, then you'll know I'm talking about this big triangle here has a base of C, and this triangle here has a base of C. Big triangle minus little triangle is this triangle, and so that must be going with C. It's the same thing we did here, right? Big triangle here minus little triangle there leaves this, which means it must go with D. That's what I wrote. Same dumb crap for E and F. So what's the big triangle that goes with little e? What's the name of that big triangle? What's the big triangle that goes with little e?
FBC.
FBC, right? And so its area minus this guy's area, because it also goes with E, right? Must be proportional to E. But what is the big triangle minus this little triangle? Well, it's this guy over here, right? So this guy over here must go with E. So I'll write that out. I'll do it in purple. I know he's green already, but we'll do it in purple. Let's do area of triangle BCG. So G should go with E. And then we'll use gray for this triangle. That means this triangle must go with F.
Can you move it down a little bit?
Yes, I can.
What does it say on the left?
This right here,
Yeah.
there. In fact, I'll zoom out because I think you can see the writing. It's just hard to see the triangle. Area of triangle looks like AVG. And you might notice we have a lot of overlapping colors. You're like, well, if it was already orange, why not just keep it orange? And that's good instinct. That's kind of the point of why we're doing this. Really, we're breaking down this big triangle into this triangle, and this triangle, and figuring out what they're proportional to. And there's going to be things that cancel out, because if you notice, we've got multiple AVGs, multiple BCGs, and multiple ACGs. So all I've done is I've said, look, large triangle, let's move this here. All I've said is, look, I've got a large triangle, and if I subtract the smaller triangle, they both go with C, right? What's left over must also go with C. Large triangle goes with D, small triangle goes with D. If I subtract them, what's left over, this triangle must go with D. And I did that for all the triangles. So this guy goes with C, this guy goes with D. A and B, this and this go with A and B. And this go with E and F. And notice there is some overlap. All right, so here's the big brain play now. Now, I know what A over B, C over D, and E over F equal, right? And so now when I multiply them all up, I can set them equal to something, right? This stuff. And this should all multiply to be 1 if this is true. So I'm going to say this. Therefore, I'm going to multiply them all up and substitute. We have A over B, C over D, E over F. Where's my thing? And we know what A over B is. It's this. It's the area of ACG, and B is the area of BCG. We get ACG in the top, BCG in the bottom. Does everybody see where I got that from? A over B equals this, right? And I'm going to do that for the rest of the triangles. I know what C and D are. station identification. Again, the whole reason I did that top part is so I can figure out what A over B, C over D, and E over F equal. That way when I multiply them, I can set them equal to something. And then if this is true, all of this should become 1 somehow. If I just used the regular triangles up here, things wouldn't have canceled and gone away, but they will with these ones. And I'll show you that in a second. Yeah.
There's no quiz this week.
Not this week, no. We're gonna correct, or not correct, but grade our quizzes on Friday from last week. There will be a quiz next week, and it'll be the last quiz of the quarter. I believe quarter ends not next week, but the week after that. Right about that?
Yeah.
Which means that you'll have a week to correct that last quiz. I won't give another quiz that will go on the quarter. That way it's not like you have no time to correct it, right? Promptly. I wanted to give a quiz this week, but it's just not possible. Early dismissal kind of screwed that up, and then maybe it's like really screwed it up. All right, so everybody see where I got these things from, right? A over B is this, C over D is this, and E over F is this. And so now if you look, I've got area of triangle ACG here and area of triangle ACG here. On the top it's multiplication, on the bottom it's division. So I'm timesing by ACG and I'm dividing by ACG. What's ACG divided by ACG? Nope, think about it. Anything divided by itself is 1, right? ACG divided by ACG is 1. Just like 2 divided by 2 is 1, 5 divided by 5 is 1, root 2 divided by root 2 is 1, pi divided by pi is 1. These two areas are the same. So they become 1. Right? They don't go away. They divide and become 1. Still multiplication. It basically goes away because 1 times anything is itself, so we can just ignore it. But I don't want you thinking it becomes 0. A lot of people think that when you cancel stuff, it becomes 0. And if that were the case, everything would literally go away because 0 times anything is 0, right? What other things do we have here that match up? That divide out? ABG and ABG. So that's dividing to get 1. Right? And then if you look, we have 2 BCGs, one on top and one on bottom, so they divide to make 1. So now we've just got a simpler way of writing this. 1 times 1 times 1. What is 1 times 1 times 1? 1. So therefore, let's use red. All this equals 1. And we're done. So what we've proven is Ceva's theorem. That says if we have 3 Cevians, and we do, and they're all concurrent, then we get a bunch of triangles, right? And those triangles, their bases, A, B, C, and D, and E, and F, their relationships multiplied all together equals 1. This is only true if those 3 segments, those Cevians, are all concurrent. Okay? So what this means is if I draw out a random triangle and I give you a bunch of numbers here, you can compare the numbers, and multiply them all together, and if they equal 1, that means all those lines must have intersected at one point. And that's going to be valuable because we're going to prove concurrency or angle bisectors, perpendicular bisectors, medians, and orthogonals, pretty much by doing this. So what did we do? Well, we matched up triangles with the same height, right? And said that they're proportional to their bases. And then we noticed, look, those also have base A and B. So they should be proportional. Well, if this is equal to that, and that's equal to that, then they equal each other. And I'm allowed to subtract them and have them equal to the third guy. We proved that with our first lemma. I know it's weird that that's true, but it's true. And then we did the same thing. We replaced this, right? We said this big triangle minus this triangle here gives us this guy. And this big triangle minus this triangle gives us this guy. these two triangles, their areas are proportional to A over B, which is what I wrote. And then I did it for all the rest. So, before I get to all the rest, how do we feel about the first part here? Lay down 100. What do we feel about 50? Yeah, you joined in late.
Yeah, can you explain the part, like, I get how you got, like, ACD and then BCD equals AB in those two parts, but then I don't get how the subtraction part works next to it.
Okay, so I'm going to go over this again. I know you already get it, but I'm going to go over it again. Remember, this triangle right here, since it shares the same height with this triangle, then their bases are proportional. We proved that with our second lemma. Remember that? Right? I did the same thing for these two that also have base A and B, right, and have the same height. And so our first lemma said that if you have three things in proportion, then you can take the first two and subtract them like this in this weird way, right? And it'll get you the third one. And we proved that as our first lemma. So if I've got three things all equal, I can take the first two and subtract them and get the third. Well, this equals A and B, this equals A and B. So it's kind of like these two equal A and B equals this, right? We've got three things all equal. So I took the first two and set them equal to last. Okay, that's our first lemma in action. Does that make sense? Okay. And then I noticed that, look, those two triangles subtracted, big triangle minus little triangle, gives us this one right here. See it? And then these two, big minus little, gets us this. So this must be true. Now I did the same thing for all the rest, right? This triangle and this triangle goes with D and C. This triangle and this triangle go with E and F. Then I multiplied them all together, right? And found out they cancel. And that's my proof. So it is a lot of writing. There are a lot of letters here. It's very much so alphabet soup, right? Because we got to write 3 letters for every triangle, and then we've got area of the triangle, right? All that crap. It's a lot of alphabet soup. But there's not a whole lot to it. Once you get it, you get it. It's not, 10 miles long of different steps. First, get your areas, right? Similar to their bases. Areas similar to the bases. When you subtract them, you get the triangles that are left over, and then you multiply them. Do we feel about 50% right now? Do I have you about 50? Okay. I don't think it's like learning a foreign language or something where it's like, oh my god, I have all this to memorize and there's so many steps and I've got to learn so much. I think it's doable. Does it look like it's a ton and really complicated? Yes, but I think when you break it down, it really just boils down to this guy and this guy go with C and D, et cetera, multiply them together and you're done. Okay? Now, this is a proof. Notice we didn't write any reasons because we did it all by algebra. Okay? I will need to see this, this, and this before you can just jump down here and say it equals 1. Okay? There aren't reasons for it because it's just by algebra. We could say multiplication property, equality, by lemma 1 or whatever, right? We're not going to do that. Okay? All in one go. Feeling okay? All right. Turn the page. All right, so somebody explain this to me. What's going on here?
It's the opposite of what we just did.
Say it again?
It's the opposite of what we just did.
It's the converse, right? So we proved Ceva's theorem, now we're going to prove the converse. So they give us that this is true, right? And we're going to prove that these must be concurrent. Now this is really what we want to get to. We really want to prove that lines are concurrent because that's going to prove that angle bisectors are, that orthogonals always are, et cetera, et cetera. Basically it proves the existence of an in-center, a circumcenter, orthocenter, et cetera, right? Yeah.
Do you have another sheet? I actually did that one on the wrong page.
Yeah, I do. This one's extra thick though, right?
I could just have one page and that'd be fine.
Okay, find the page you want. All right. So we're proving the opposite. So we're given this to start with, and then we're going to prove that these are concurrent. Cool. All right. Hold on 1 second. Do I have the visual? Hold on once. All right, I want you guys to take a look at this. Instead of walking you through it, I want to see if you guys can understand it. Let me grab this and go here so this so here's their proof of Ceva's theorem of converse. It says, construct a triangle that has cedians, right, et cetera, right? We have. Now, they're not assuming that they're concurrent, but they're going to prove that they are. So what they're saying is that if we have Ceva's theorem, right, we know that these all multiply together should equal 1, right? That's what's given to us. They wrote it out with different line segments, right, using Vx and stuff like that. I used A, B, C, D, and E, F, okay, little letters. So they said, let Y, this point right here, be a point on AC that is not the same as this one. So notice we have a CD and B, Y prime, right? And we have another cedian that they're drawing that they're letting be ready to Y. So if this is true, that this works without these being concurrent, then I should be able to draw another cedian and it should end up being true as well. That's the logic. But of course that won't be true. What we call this is a proof by contradiction. Instead of proving something is true, we assume that it's true, right? And then what happens is we show that, well, if we assume it's true, it means like math breaks. And math should not be allowed to break, right? And so therefore it must not be true. This is a different type of proof than we've done before. Again, proof by contradiction. We're not proving it true. We're proving that if it was true, it would mess up math. It would be impossible, right? So we assume it is, and show that it would break all of math, and therefore that means it must not be true. Because if it was true, math would work. We know math does. That's the idea. We'll talk about that more tomorrow. Oh, I forgot.
Do you
We're
want
going to be in a short class period. You don't remember pass it.
do you want the extra pages that I had, or should I throw them away?
You can throw them in.